Guys, welcome back to this channel. Thank you very much guys for the encouragement. Please subscribe, like and drop a comment if you really like the video, and please hit the notification button to subscribe anytime I upload to get notified anytime I upload a new video. So today we're going to be looking at buoyancy and flotation. This is another topic in fluid mechanics which we are going to be looking at today. So before we solve the problem in front of us, which is a cylindrical buoy of diameter 2 meters, height of 2.5 meters, weighing 2,000 kilograms, flows in sea waters, prove that it will be unstable. Now take the density of seawater to be 1020 kilogram per meter cube. So before we solve the problem in front of us, I'm going to give a brief revision on buoyancy and flotation, or what buoyancy and flotation is actually talking about. So now, what is buoyancy or what is flotation? Flotation is basically a substance that does not, let's say, when you say a substance floats in a certain medium, meaning that the substance does not sink, neither does it float at the surface. It is basically in a certain depth, or immersed in a certain depth above the level or above the surface of that medium. So now, what does it mean, or what is buoyancy and flotation actually talking about? Now, when a substance is immersed in a fluid and does not sink, it floats, right? So now, when a substance is immersed in a fluid, it experiences a pull. Now, what I mean by a pull is it experiences an upward force. Now, take for instance, this is a medium of water, right? Now, there is a body immersed in this water, which is a rectangular body immersed in the water, right? Now, this body immersed in this medium or fluid will experience a pull, an upward force, which we call buoyance force, or force of buoyancy. So now that force of buoyancy will be acting upward, not to make it not to sink, or sorry, not to make it not to sink, in making the body to float. Now it is said that this upward force, or this buoyant force, is equal to the weight of this body itself. Let's consider the weight of the body to be W. Now this buoyant force is equal to the weight of the body, but they are acting in opposite direction. So when a body is immersed in a fluid, it experiences an upward force, which is called the force of buoyancy, which is equal to the weight of the body. Now, when the body is immersed in a fluid, it displaces a certain volume of water. The weight of the body itself in the fluid will displace a certain volume of water. So that's why we say the weight of every body immersed in a certain fluid is equal to the volume, it is equal to the weight of water displaced by the body. I'll repeat myself. I said the weight of a body immersed in a fluid is equal to the weight of water, weight of fluid displaced. So the weight of this body itself will displace a certain weight of fluid. So that is why the weight of the body is equal to the weight of fluid displaced. So if the weight of the body, which is W, is equal to the weight of fluid displaced, that means the buoyant force is also equal to the what? The weight of fluid displaced. So either the weight of fluid displaced or the force of buoyancy is equal to the weight of water displaced. So is that taken? So this is basically the brief revision on force of buoyancy. I repeat myself. I said when the body is immersed in a fluid, it experiences two forces going in opposite direction: the weight of the body and the force of buoyancy. These two weights are equal to the weight of water or fluid displaced. That's it. So now let's look at the problem in front of us that says a cylindrical buoy of diameter 2 meter and height of 2.5 meter. So the first step to solve something, or yeah, is to solve a question under buoyancy and flotation, is to basically represent it in a well-defined diagram. So now they said a cylindrical buoy, meaning a cylindrical body. So now let's consider a cylindrical body in its vertical axis. So if this is the plan of the cylinder, right, then this will be the front elevation of the cylinder. Is the plan of the cylinder, and this is the front elevation of the cylinder. So the cylindrical body of diameter 2 meters, so this is having a diameter from here to here, is having a diameter of 2 meters, and basically it's the same thing also here, because this is plan and this is the front elevation of 2 meters and a height of 2.5 meters. The height of the cylinder says 2.5 meters. Now it floats in seawater. For example, the cylinder floats in seawater. When something is floating, it hasn't sink yet. Now it floats in seawater. Is that taken? So now they said we should prove that it will be unstable. Now I forgot to explain what I mean. What does it mean by stable and unstable? When a substance is stable. Now when the substance is stable in a particular medium, its metacentric height is positive. But when it's unstable, its metacentric height is negative. Now, what is a metacentric height? Metacentric height is basically the distance between the center of gravity and the metacenter. Now, take for instance, this is a body in a fluid, right? Body in a fluid. We have the center of gravity, which the weight is acting, and we have the center of buoyancy, which the force of buoyancy is acting. The center of gravity is where this weight is acting, and if the center of buoyancy is where your force of buoyancy is acting. So now when this substance, for example, is immersed in this liquid and it gives a slight displacement, for example, gives a slight displacement. Now this is your center of gravity and this is your center of buoyancy. Now there will be a new center of buoyancy because the substance will adjust, because the force of buoyancy will not be acting at this point again, it will be acting at your new center of buoyancy. Now we call this, we draw a vertical line also. Now where this vertical line cuts this line is called your metacenter. So like I said, when it's given a slight displacement, your center of buoyancy shifts to a new position in which your force of buoyancy will act, Fb. So drawing a vertical line like we did here also, it will intersect at your previous line, which you call it the metacenter. So the distance between your center of gravity and your metacenter is called your metacentric height. So a substance will float or will be stable when immersed in a fluid if the metacentric height is positive, and will be unstable if the metacentric height is negative. So basically, to prove that this body will be unstable, we need to get the metacentric height. So if the metacentric height to obtain is negative, then it is unstable. So now let's solve. So what comes next is the formula for calculating metacentric height. So what is the formula for calculating metacentric height? Formula for calculating metacentric height, which is Gm, is equal to I. This I is called the moment of inertia, or the second moment of area, divided by the volume of liquid or the fluid displaced minus Bg. Now I'm going to explain what Bg is. So now first, like I said, when a substance is immersed in a fluid, there is a center of gravity and there is a center of buoyancy. Now let's call this point O, this bottom point O. Now like I said, when a substance is immersed in a fluid, it will be immersed at a certain depth. And this is called height of immersion, meaning that the depth in which the fluid was immersed in the liquid, let's call it H bar. Now this is the depth of immersion. Now just follow me step by step, you will really understand how I'm going to solve the calculate the metacentric height. So basically, to calculate the metacentric height, I need the moment of inertia, I need the volume of water displaced, I need BG. Now BG is the distance of the center of buoyancy and the center of gravity. So first, let's calculate my moment of inertia. So to calculate the moment of inertia of a cylinder is pi d raised to the power 4 divided by 64. So which gives me pi times the diameter, where d is the diameter. The diameter they gave me here is what? 2 meters. So 2 raised to the power 4 divided by 64, which is equal to 0.75. So now we've successfully calculated my moment of inertia. Now the second step I have to do is to calculate my volume of water displaced. But first, to calculate my volume of water displaced, which says my volume of water displaced V is equal to volume of a cylinder is what? Volume of water displaced is equal to actually the volume of a cylinder immersed in a fluid. Now let me repeat myself. I said the volume of water displaced, seawater displaced, is equal to the volume of a cylinder, in the fluid or in seawater. So basically, the volume of this object, or the volume of this object in this particular medium, the volume it is occupying in this particular medium, or the volume it experiences. There's actually, when the substance is on the air, it has a different volume than when it is in a particular fluid, a particular medium. So the volume of that substance in that particular medium is equal to the volume, will be equal to the volume of water displaced. Likewise, the weight of water displaced will be equal to the weight of the cylinder in that medium, in seawater. So basically, these are the two assumptions we use basically in solving buoyancy and flotation. The volume of seawater displaced is equal to the volume of cylinder, or the volume of any object in that particular medium, or the weight of water displaced will be equal to the weight of the seawater in that particular medium. So basically, to get my volume of water displaced, that is my V, will be equal to the what? The volume of cylinder in the seawater, in that seawater. So what is the volume of cylinder, which is what? Pi d square over 4 times h is the volume of a cylinder. So now, where h is my, not the height of my cylinder, but the depth of immersion of my cylinder in the fluid. So it's basically called h bar. So now I can actually calculate the volume of my object in this particular fluid when I don't have h bar. So let me calculate my h bar. So since we're given, now to calculate my h bar, I can make use of my second assumption. Since we're given my mass, that is the mass of my cylinder, to be 2000 kilogram, I can calculate the weight of my cylinder to be what? 2000 times 9.81, which gives me 19620 Newton. Now, like I said, we're going to be making use of the second assumption, which is the weight of cylinder is equal to the weight of water displaced. So now this gives me my weight of cylinder. Now, weight of cylinder, which is 9.620, is equal to the what? The weight of water displaced. Now, what is the weight of water displaced? Now, you know that weight is equal to what? Weight density times volume, right? Because weight density is equals to weight over volume. Weight density, which is equals to weight over volume, and my weight here becomes weight density times volume. And you know, weight density is mass density times acceleration due to gravity. So, which gives me my weight density, which is my weight over volume, becomes my weight density times volume. So that's how we got this formula. My weight of water displaced is density times volume times acceleration due to gravity. So since my weight of water displaced is this, which is actually a standard formula for calculating weight of any fluid or any medium, then my weight of cylinder, which is actually equal to the weight of water displaced, will be equal to density times volume times acceleration due to gravity. So the density of my seawater, which they gave me in the question to be 1020 kilogram per meter cube, then we have 1020 times the volume of water displaced, where V here is the volume of water displaced. If this is the weight of water displaced, and weight of water displaced is equal to the density of water times the volume of water displaced times acceleration due to gravity. I'm going to repeat myself. This is the weight of water displaced, which is equal to density times volume times G. Now this is the density of water displaced, the density of water displaced times the volume of water displaced, and times the constant, right? Now this is the volume of water displaced. Remember, we call it V. So where V is my volume of water displaced. So now my volume of water displaced, which is actually equal to my volume of cylinder, the volume of my cylinder, which is what? Pi d square divided by 4 times my h bar. Remember, which we assume to be here, to be this. The volume of water displaced is equal to the volume of my cylinder, which is pi d square divided by 4 times h bar. So which we have here times my constant 9.81. So basically what we are trying to do, we can actually calculate my volume of water displaced from here and put it in my equation, but we actually want to calculate my h bar. That is what we want to calculate. So then we can easily get the distance or the space between my point of center of buoyancy and my center of gravity, which is BG. So to calculate my h bar from here, I have 1020 times pi times my diameter, which they gave me as 2 square, divided by 4 times my h bar times 9.81. So making my h bar subject of formula, I have 19,620 divided by 1020 times 9.81 times pi times 2 square divided by 4 equals h bar. So simplifying all those, we have my h bar, or the depth of my immersion, will be equal to 0.624 meters. Now that's my h bar. So then we have successfully calculated my depth of immersion to be what? 0.624 meters. Then I can easily calculate my BG. But first, let's calculate my volume of water displaced. Now, since I've calculated my h bar, I can easily substitute it here to get my volume of water displaced. So therefore, my volume of water displaced, which is pi d square divided by 4 times my h bar, is equal to pi times 2 square divided by 4 times 0.624, which gives me 1.96 meter cube. Now I've successfully calculated my volume of water displaced. Then what remains is to calculate my BG. So to calculate the distance between my point of buoyancy and my point of gravity. So how do we get it? First, you know that the distance between BG is equal to the distance from 0 to G minus 0 to B. What am I trying to say is that the distance from here to here minus the distance from here to here gives me the distance between B and G. As simple as that. That means the distance from O to G minus the distance from O to B gives me the distance from B to G. I'll repeat myself. The distance from O to G minus the distance from O to B gives me my distance from B to G. So how do I get the distance from O to G? Let me write it out first. I said BG is equal to OG minus OB. BG is equals to OG minus OB. So what is OG? Now OG is basically the center of gravity, right? The height of the center of gravity. And you know the center of gravity is always at the center of every medium. So since we have the height of the cylinder to be 2.5, my OG is 2.5 divided by 2. The center of gravity is always at the center of every medium. So since the height of my cylinder of gravity, since the height of my cylinder is 2.5 meters, then my center of gravity will be at the center of my height, which is 2.5 divided by 2. So my OG, that's the distance from here to here, my OG is what? 2.5 divided by 2, which gives me 1.25 meters. Now my OB, which is at this point, my OB is basically this. Remember, when an object is immersed in a fluid, it immediately has point of flotation or point of buoyancy. So this point of buoyancy is basically the center of gravity of every object in a fluid. So my OB is basically my height of immersion divided by 2. Just like my center of gravity is the height of my cylinder divided by 2, my OB is my height of immersion divided by 2. Basically, this B here is the center of buoyancy, which is also the center of gravity of every object in a fluid. If I have an object, for example, a cup, which has a center of gravity also, before immersed in a fluid, when immediately is immersed in a fluid, it has a center of buoyancy. Now, this center of buoyancy is the center of gravity of that object in that medium. So my OB becomes my height of immersion, which we got as 0.624 meters. My height of immersion 0.624 divided by 2, which gives me 0.312 meters. So my OB. So definitely I can easily get my BG, which gives me my OG, which is what, 1.25 minus my OB, which is 0.312. Then this gives me 0.94 meters. Now I can calculate my metacentric height. Then, because I have my BG, I have my volume of water displaced, I have my moment of inertia, which we got here to be 0.785, then I can put it back in my formula to get my metacentric height. So we said my metacentric height, which is GM, equals moment of inertia divided by volume of water displaced minus BG, and the moment of inertia we got, remember, was what? 0.785. 0.785 divided by the volume of water displaced, which we got to be 1.6 meter cube, which is 1.6 meter cube, 1.96, minus my BG, which is what? 0.94. So simplifying all this, we have 0.85 divided by 1.96, we have 0.4, then minus 0.94. So 0.4 divided by 0.94, we have minus 0.59. Meters. So you see that the question given says prove that the body will be unstable. So, and I said when the metacentric height is negative, the body is unstable, meaning that the center of gravity is below the metacenter. Thank you guys for watching. Please subscribe.